We will have a look at metal displacement reactions, which is covered in a previous video. We're going to look in them in a bit more detail, and we're going to see that really they are redox reactions. Okay, so just to recap what redox is, a new definition a bit in terms of electrons. Here we've got it up here. Oil rig, oxidation is loss of electrons, reduction is gain of electrons. Okay, so here we've got a reaction of, should be pretty familiar to, putting zinc in copper sulfate solution. So here we've got a bit of gray, silvery grey zinc, put it in blue copper sulfate solution, and the blue color fades, replaced with zinc sulfate, and the piece of zinc is covered with reddy brown copper. Okay, now that happens because we look at the reactivity series here. Zinc is more reactive than copper. Okay, so you had zinc to a copper compound. You displace the copper, you form a zinc compound, and you end up with copper metal. Now that if we just like when you're in year 9, the say, oh, the zinc is more reactive, it takes the sulfate off the copper, and that's not really a very good way of looking at it, because it's not really what happens, as we'll see in a minute. Okay, so let's think about ionic solutions. Ionic compounds when they're in aqueous solution, like copper sulfate and zinc sulfate. Okay, so if you think, let's think of sodium chloride. Right, now sodium chloride as a solid exists as an ionic lattice. When you dissolve it in water, the ions just separate completely. They've got nothing to do with each other. You get sodium ions and negative chloride ions floating around in solution, each one with nothing to do with the other one. Similarly, when you get copper sulfate solution, well, copper is an ionic compound. When you dissolve it, you've got copper 2+ ions go floating around by themselves, and you've got the sulfate ion, that's SO4, with a 2- charge on it. They're floating around. So people get a bit confused about sulfate ions because it's SO4 and then 2-. 2- refer up there, superscript is with charge. This 4 here tells you how many oxygens are joined onto the sulfur. Okay, so it's sulfate ion is SO4 2-. Right, so let's rewrite this equation now as an ionic equation. So what I mean by that is we're going to, anything which is in aqueous solution, which is dissolved, we separate it out as the ions, because that's it's a more realistic representation of what's happening. So we get zinc solid there. React that with copper sulfate. So copper sulfate in solution is, you have copper 2+ ions and SO4 2- ions floating around. They've got nothing to do with each other. Incidentally, it's the copper 2+ ion that gives the solution its blue color. And when the reaction is finished, right, well, you've got zinc sulfate, and that is an ionic compound, so you can split that up into zinc Zn2+ ions and sulfate ions, SO4 2-, and copper atoms. Right, so let's see what's happening there. Now we're going to look for so-called spectator ions. Now spectator ions are things that don't change as you go from the left-hand side of the equation to the right-hand side of the equation. So you can see there, hopefully, that the sulfate ions, that and that, they don't actually do anything. They're just floating around there. So we're going to rub those out so you can see more clearly what actually is happening, what's changing. So if we look at the change here, we can see that the zinc has changed from zinc atoms into zinc 2+ ions. So that means it must have lost, each zinc atom must have lost 2 electrons. So in other words, it's become oxidized. And where do those electrons go to? Well, if you look at the copper, it becomes evident, because copper changes from a Cu2+ ion to a copper atom. So that has gained 2 electrons. So that, in our definition, oil rig, oxidation is loss, reduction is gain, the copper has become reduced. So this is a redox reaction. And let's have a little think about it more. Well, we know zinc is more reactive, so that really doesn't want to have the electrons. It wants to become a zinc ion. so it loses electrons, whereas copper is not that reactive, so it doesn't mind, copper 2+ doesn't mind accepting electrons and turning back into the element, into copper atoms. Okay, let's have a look at another reaction then, very similar to that, just to illustrate it further. Right, what we got here is magnesium this time, which is more reactive than zinc. We're going to add magnesium to a zinc compound in aqueous solution to zinc chloride. Okay, so here we have got a piece of magnesium ribbon, got a solution of zinc chloride, which is colorless. After the reaction, you can see on the surface of the magnesium, you've got little bits of black zinc on there. Okay, so once again, let's rewrite that equation as an ionic equation so we can see what's going on. So anything which is in aqueous solution, any ionic compounds, we're going to split them up into the ions. So first of all, we've got magnesium metal there. Now zinc chloride we can split up. It's an aqueous solution, ionic compounds made of zinc 2+ ions and chloride ions. Okay, now that's where the ZnCl2 is a little bit misleading when the formula is written like that, which it is written like that, because it makes it look like the chlorines are stuck together, but of course they're not. They're two completely separate chloride ions. They have nothing to do with each other. If you wrote Cl2-, that would imply that you've got two chlorines covalently bonded to each other, with the whole thing having a minus charge on it, which of course is not what happens. So yeah, you just need to be careful to write that down. It's 2Cl- there. And they're both in aqueous solution. And they're going to change, right? You've got magnesium chloride on the other side. So again, that's Mg2+ and 2Cl-. And we've got zinc metal. Okay, so I am now going to, let's look for the spectator ions. Well, hopefully you can see it's the chloride ions. Nothing happens to them. They stay the same as two chloride ions. So we can rub those out to see what's going on. So we can see now what's happening really then is the magnesium atoms are turning into magnesium ions. So they've lost 2 electrons. Oxidation is loss, so that is oxidation, or rig. And the zinc ions, well, they turn from zinc ions to becoming zinc atoms. So what do? What happens there? They gain 2 electrons. So they have become reduced. Okay, so once again, the more reactive metal, magnesium in this case, doesn't want the electrons, and it makes the zinc ion take them on. Okay. This is incidental to this topic, but you might think, right, you've got a flow of electrons from magnesium to zinc. That sounds a bit like an electric current, and you can actually make a battery or electrochemical cell. You get a piece of magnesium, connect it to a piece of to the zinc compound with a wire, and the electrons will flow from the magnesium to the zinc, and you can make the electrons, light up a light bulb or something like that on the way there. Okay. Right, now let's have a look at the reaction between magnesium and hydrochloric acid. Right, so this is not a metal displacement reaction because we're not reacting with a metal compound, we're reacting with hydrochloric acid. Now, we've got hydrogen in the reactivity series here, and we can see that hydrogen is less reactive than magnesium, and it's extremely similar to what happens in the metal displacement reaction. So let's just have a look. We've got magnesium atoms. Now, hydrochloric acid, all acids, I'm going to write it a bit further down, I've run out of space. All acids give up H+ ions when you dissolve them in water. They ionize, they turn into H+ ions and a negative ion. So we have magnesium, solid, and hydrochloric acid is H+ ions, aqueous, and they're the things that make it acidic, and chloride ions also. Now, because in the balanced equation we've got 2 hydrochloric acids here, I need to put 2 H+ there and 2 Cl- there. That forms magnesium chloride, which is an ionic solid, so we're going to separate it out to Mg2 plus aqueous and 2Cl minus, not Cl2 again, and we're going to get hydrogen gas H2. Right, so let's look for the spectator ions once more. The spectator ions are, got two lots of chloride. The chloride ions, they don't do anything yet. So we're going to get rid of those. And what can we see we've got now? We've got magnesium atoms turning into magnesium ions. So what have they done? They have lost 2 electrons. So they've become oxidized. And the hydrogen ions, well, you've got 2 H plus ions, and each one has gained an electron to form a hydrogen atom. And those 2 hydrogen atoms then stick together to form a diatomic molecule. So they have gained electrons. So the hydrogen has become reduced. So hopefully you can see with our reactivity series then, really, a metal is more reactive. These ones, when it wants, they really want to lose electrons. The metal atom really wants to lose electrons, the sodium particularly, whereas copper doesn't really care about losing electrons. It's not very reactive. And converse of that, if you get the metal ions, so if I write down the ions you have for these, so sodium forms an Na plus ion, magnesium forms an Mg2 plus, zinc 2 plus, iron 2 plus usually, sometimes 3 plus, hydrogen H plus ions, and copper 2 plus ions. Well, these positive ions, copper, they've all got some tendency to accept electrons. The copper, that's quite keen on accepting electrons, whereas I think the sodium at the top there really does not want any electrons at all. Okay, so you've got 2 different trends, one gaining electrons, one losing electrons there.